So this is our second lecture in vapor power cycles. Last time we talked about the Carnot vapor power cycle. Hopefully it was a little of a review, some maybe not, from Thermo 1. And we use that as a gold standard, as sort of the foundation of moving toward practical vapor power cycles. And we then can compare and actually use the knowledge out of the Carnot to help guide why the Rankine cycle has been modified the way it is in real power plants to enhance performance. So when we say the Carnot vapor power cycle, do you recall the four components? Yeah, the turbine, condenser, pump, boiler, from memory. And then we have the states. Put them in this order so that one is in the upper right, state 2 is in the lower right, state 3 is in the lower left, and then upper left to state 4. Because if you line it up on a property diagram, the temperature entropy diagram, you tuck it under the dome, state 1, upper right, state 2, lower right, state 3, as well as state 4. Why do we like the temperature entropy diagram? Visually, it helps us visualize something special about that cycle. That's right. Why did we like the pressure volume diagram? Because if I took a system and I expanded it from state 1 to state 2 along a line indicating a process, a sequence of states which were all in equilibrium, quasi-equilibrium states, we could interpret the area under that curve as something special on a PV diagram. What was that area under the curve? The work. This shaded area is the image of the work per unit mass if I put this on a lowercase v. Can you compare the expansion from state 1 to state 2 along path B compared to path A? Which one gives you more work? A. You can tell visually, right? Could you tell from path from 1 to state 2 here? Path C, you know, can you compare path A, B, or C? Which one gives more work? C, the larger area under the curve. Well, why do we like the temperature entropy diagram? Can we interpret the area under the curve on a temperature entropy diagram as anything? Q, it's the rate or the amount of heat transfer. So if you go through the boiler, what's happening? We're adding heat in the boiler. That's happening between 4 to 1. 4 to 1. And so if I integrate T ds, lowercase s, specific entropy, is that lowercase q coming into the system in the boiler? If I go from state 4 to state 1? Exactly, it is. And so we can draw in that area just like this. It goes all the way down to 0, just like the PV diagram went all the way down to absolute 0 pressure here, 0 Kelvin. Now, where do we reject heat out of this cycle? In the condenser. Okay. What does the process look like in the condenser? It goes from state 2 to 3. It goes from an S2 to an S3. Which entropy is greater? At state 2 or at state 3? State 2 has a... And if you go back to calculus, I know that they didn't teach everything in calculus, but whenever you had to do an integral f dx, right? You always went from x1 to x2. You always went from x1 less than x2. You always integrated in the direction of increasing x. Look back and think about it. Is there anything well, first of all, if f is the function you integrate, and that is the function that if you differentiate cap f, you get lowercase f back again. I'm trying to remember some of the calculus jargon I was exposed to. Then you can evaluate this integral by evaluating cap f at x2 minus cap f at x1. Does that resonate with anybody? Like, oh, I kind of remember that notation in calculus. Well, what would it mean to actually integrate not from x1 to x2, but x2 to x1 f dx? Can you tell that that's just going to be the negative of the integral of x1 to x2 dx? It's like the subtraction. So visibly, I can see that if I'm going to integrate from state 2 to 3, integral t ds, that's not a positive q in, that's a negative q in. It's out of the system. And that's physically consistent. So this all shaded in red is what's coming into the system, into the boiler. This, which I'm just visibly seeing the magnitude of the area, from 2 to 3, the area under that curve, that's out of the system. The difference is, what's the difference? What's enclosed by the cycle? What's enclosed in the box? And so the Q net is Q boiler plus Q condenser, where this is going to be a negative amount. All right? And so visibly, this area here is the Q net of the cycle. That's why we like the temperature entropy diagram, one of the reasons we like it. So the Q net of the cycle is also equal to the work net of the cycle. Is that true? Where did we get that from? Conservation of energy, that's right. So this cycle is operating steady state. You know, it's a cycle. It's repeating itself. So the net amount in of energy by heat has to be equal to the net amount of energy out by work. So Q net's equal to W net. So what we can see right away, visually, we can see the effects of different things on the cycle. Somebody says, I've got a Carnot cycle where TH is this value and TL or TC is this value. Sometimes I use TC for cold and sometimes TL for low. Okay, low temperature, high temperature. What happens if they drop TC but leave TH alone? Is that good for performance or bad for performance? Good. It's good for performance. And graphically, we can see it because what is the thermal efficiency? The thermal efficiency is Q net, which is W net, divided by Q boiler, which the boiler is everything underneath going from 4 to 1. And so the area ratio, you get a higher percent of that heat brought into the boiler goes to the produced work, net work. How about this? Same thing. If you could increase TH, that will actually help as well. The thermal efficiency of the Carnot vapor power cycle will go up. Okay. You can see that in equation because 1 minus TL or TC divided by TH is equal to the efficiency. And so what do you want to do to TC? Decrease it. What about TH? Increase it. Good for thermal performance. All right. Let's press forward. Well, we put that on a temperature entropy diagram, and it turned into a nice box. And notice at state 2, what is the quality? It's not 100%, maybe it's 70%. What about the quality at state 3? The quality at state 3, maybe around 30%, 35%. We talked about that. All right? What's happening between 1 and 2? You're going through the turbine. What about 2 to 3? We're going through the condenser. What about 3 to 4? We're going through the pump. And then 4 to 1, boiler. True? Very good. We solved the problem. We put up some numbers. One of the takeaways I left you with last time was Organize your work. Think about making a table of, what is this a table of? Properties. Think about making a table of, what's this a table of? Heat and work transfers for each of the 4 components. So analyze the energy balance for each of the 4 components. And then what's this? The bottom line, the sort of metrics that everybody wants to talk about, right? I want to talk about what is the net work per unit mass going through the cycle. Is that high? That's good if it's high. If it's low, it's not so good. How about the back work ratio? I'd like a low back work ratio. How about the overall thermal efficiency? I'd like that high. I'd like that high. And then notice that when you do the calculations, these two are exactly the same, although the method to get this thermal efficiency is W net divided by Q in the boiler, W net divided by Q in the boiler, and numerically it gives you the same as 1 minus Tc over Th for the Carnot vapor power cycle. Why is the Carnot vapor power cycle not practical? Why is that pump the Achilles heel? They say, this is great, let's go build one. Engineers, here's the job, go build it. You say, I could do a pretty good job of that turbine and the boiler and the condenser, but that pump, I can't do it. Why is the pump not practical? Because it's not being fed 100% liquid. You feed a compressor 100% gas, no liquid. You feed a pump, just the opposite, 100% liquid, no vapor. And so this is the difficulty. Why did we feed it? Why did we stop on the temperature entropy diagram at state 3 and put it through the pump? It's because we really wanted state 4 where? Saturated liquid. All right. So that's why you can't build a Carnot vapor power cycle. This pump was the difficulty. So what do? They modify the cycle slightly, and that's how you get the Rankine cycle. So before we talk about the Rankine vapor power cycle, here's a little summary of who we recognize as putting his name to something so he's remembered because of his great contributions in science and engineering. These are the years he lived, 1820 to 1872. Again, just like Sadi Carnot, he died too young. Sadi Carnot was only, 36? He's only 52. Yeah, you may think, hey, 52 is long. That's old. Nope. Not when you're beyond 52. That's too short. He's Scotland, had a very wide range of interests. In 43, he produced some seminal work in fatigue and metal railroad axles. In 55, he was appointed by Queen Victoria Chair of the Civil Engineering and Mechanics at University of Glasgow. And in 59, that's why we remember him in this class, he issued this book, which is a copy. And you can read Google Books as well as probably buy a copy or a reprint somewhere. A manual on the steam engine and other prime movers. He's remembered and honored by his name attached to that temperature scale, the Rankine temperature scale. Also, this is what here is the vapor power cycle. And even there's a lecture series in geomechanics with an honorary award or distinguishment in his name. There's other things. It's a long list, but this is who we are honored by calling it the Rankine vapor power cycle. So what did we do? First of all, the word ideal is often thrown in front of the Rankine power cycle. What do you think the word ideal means in front of that word? Is it that there are no irreversibilities in the cycle, or that the turbine and the pump are internally reversible? A or B? Best answer. A or B? B. Basically, the isentropic efficiency of the turbine is left at 100%, and the isentropic efficiency of the pump is left at 100%, meaning there is no irreversibilities in the turbine. There is no irreversibilities in the pump. That's what the word ideal means. Before we solve the problem, I want to talk about how do we modify then to make this pump work. What do we do to the cycle to make it practical? This used to be the saturated liquid state, state 4. What we do is we let the condenser do the whole work. Let the condenser do its great job of condensing such that what comes out of the condenser isn't some 30% quality with some vapor. It's going to be saturated liquid. So saturated liquid, this no longer is saturated liquid. State 3 is saturated liquid. So on our temperature entropy diagram, we're going to take and condense all the way, well, we're starting right here at state 2, all the way over to state 3. That makes sense? All right. Now, once we know what we're doing, then we can feed that into a pump. So here would be a problem. So instead of a Carnot vapor power cycle, it's an ideal Rankine vapor power cycle. The same working fluid, the same high pressure of the boiler, the same low pressure of the condenser, and do the same thing. Get me the work and the heat for each of those components. A lot of it will be the same steps. Okay? It'll be the same steps. It's only when you get to state 3. What's special about state 3? It's low pressure and it's saturated liquid coming out of that condenser. And so if I needed to know, well, the pressure and the temperature, the quality is going to be 0, the specific volume and the saturated liquid specific volume, enthalpy, the H of F, the saturated liquid enthalpy, the entropy, S of F. I'm trying to modify that table in my mind of what's going to change. State 1 and state 2 are the same. Then what happens at state 4? So I have that pump. I'm feeding it saturated liquid. What about state 4? Could state 4 be saturated liquid? Let me think about this for a minute. So here is my temperature entropy diagram. State 1 didn't change. What comes out of the boiler? Saturated vapor. State 2 didn't change. State 3 is over here. And I'm going to pause. Don't shout it out. I'm going to walk around and I want you to show me on your rendition of a temperature entropy diagram, where is state 4? Where is state 4? It's going to be the output of the pump. We knew where state 4 was before, right? But we changed where state 3 is, and I'm showing you where the new state 3 is right there. Isn't state 3 saturated liquid at the low pressure? Now where is state 4? All right. Some students will put state 4 kind of where it was before. Hey, around that vicinity is state 4. Some students will put state 4, they'll say, you know what, it's kind of in this vicinity. I think state 4 is around there. Some students put state 4, I've even seen state 4 kind of over in this vicinity, or somewhere in this vicinity, or somewhere in this vicinity, or somewhere in this greater vicinity. Hey, it's somewhere out there. I'm just going to lay it out there and you pick, right? So of all of those, if you want to label them or number them, which one do you really think is where state 4 is? Who's a brave soul? Why is it not up here? But a lot of people will put it up there. Because this would show like no change in entropy. That's true. Is the pump reversible in our assumption and analysis? And is there any heat transfer with the pump? So people are saying, it's isentropic. I think state 4 is along this line. You're absolutely correct. You're absolutely correct. Sometimes they'll draw it kind of over this way, there's state 4, but really it can't be. It needs to be, if you're artistically correct, it needs to be straight up and down on that line. True? So you can rule out here. No, that's not where state 4 is. Not over here and not over there. Okay? So it's going to be along this line. So is it closer to maybe coming out with a temperature in the vicinity of 300? Or closer coming out with a temperature of 200? Or closer coming out with a temperature 100? Or what? Which one of these three choices for the outlet temperature of the water out of the pump would be closer? I'm going to pause, I'm going to stop, I'm going to walk around. So the consensus of the class is a lot closer to 100 than it is to 200 or 300. That's a great consensus of the class. Somebody want to explain to me why? You'll try it. Go ahead.
Because it has to reach the line of constant pressure.
Because he's thinking this line of constant pressure, this is the line of 8 megapascal. It comes down. Does it stop right there? Is this the end of the line of 8 megapascal right here? Where does the line continue? It goes down. Did I plot it? Did the software plot the line in this vicinity?
Yes.
It's actually plotted. Did you know state 4 is given in this illustration with a circle, just like state 1 is a circle, just like state 2 is a circle, just like state 3 is a circle? Can you see the circle, the same size for state 4? You can, if you really look. But I'm going to zoom in. Where am I going to zoom in? I'm going to zoom in right there. There's my zoom in the software. So let's orient ourselves a little bit. The thick red line is the line of saturated states, all saturated liquid. That's part of the dome. This line cutting across is a line of constant pressure of 20 kilopascal. When it hits to be saturated liquid at 20 kilopascal, the actual temperature for TSAT is 60.1. Can you see that? This is 60 degrees C. This is 61 degrees C, 62 degrees C. It's about 60.1 degrees C. Does the line of 20 kilopascal just sort of die and stop right there? Or is it also on this plot continued? It's also on this plot continued, but it's underneath the red line. All right, what's this blue line right here? A different pressure. It's not 10 or 20 kilopascal. What's the pressure of that line? 8,000 kilopascal or 8 megapascal. So you are absolutely right. It was constant entropy. And the outlet of the pump is right there. Can you tell me roughly the temperature of the water coming out of the pump? It went in at 60.1 degrees C. 60.4-ish. 60.5-ish or something, right? Can you see that? So how much was the temperature increase in the water going through the pump? Less than a half a degree C. Is the purpose of the pump to boost the temperature of the water going through it? No. What's the purpose of the pump? It's obvious, to boost the other property of interest, the pressure. The outlet pressure of the water going out of the pump much higher. This is always a challenge for students. Oh man, what happens after that pump? It must come out 300 degrees. No, it's not 300 degrees C. And this is one of those parts where you'll find faculty, and I think a lot of you have already knew this, but they'll say, you know where? They're a state 4, I'm sorry. And what will they do by putting state 4 so far away from state 3? They'll make it clear that state 4 is in that vicinity. But they've grossly exaggerated the temperature at state 4. The temperature at state 4 is essentially the same as the temperature at state 3, plus a little, half a degree. True? Do you see that? All right. So we continue on and we solve this problem. If you solve this problem, sometimes they'll change the schematic a little bit. They'll put a round device for a pump. Maybe they'll make the boiler nice and tall. Why would they do that? Well, if you ever saw a pump, a centrifugal pump, they look kind of like you bring the fluid into the middle of a round thing and it's slung out and captured on the side and thrown out. That way, it's more representative of what a pump may look like in a schematic. What about the boiler? Why do they make it so tall? Well, if you ever seen a real boiler where they're burning coal at a coal-fired power plant, it's like walking into a hollowed-out, multi-story building. And it may be 4 stories, 5 stories tall, and all it has is a bunch of tubes carrying water around the walls. And a huge fireball will be, you can look inside when it's running, you can walk inside when they shut it down for maintenance. But it's huge hollow device, very tall. And then the turbine, sometimes they'll just draw it like this, and they'll show it coming in and then expanding through different stages of the turbine. But if you just draw a box for all these, it's equivalent for this course. Okay? And then the condenser is just another box. But what we do is we put state 3 to be the saturated liquid. Notice the temperature at state 3, around 60.1. And how do we analyze state 4 then? What 2 pieces of information fix the state? Well, it's really pressure and entropy fix the state. But I really need the enthalpy at state 4. How do I get the enthalpy? How do I make that calculation? How do I get it? Let's say enthalpy at state 3, that's H of F at the 20 kilopascal coming out of the condenser, saturated liquid enthalpy. How do I calculate? I'm going to walk around now, pause, walk around. How do I calculate H4? Show me in an equation or sequence of equations on your notes how you would calculate H4. Well, a couple of you remember this equation coming out of Thermo 1. And what is that key equation? Well, that the enthalpy will be equal to the enthalpy at state 3 plus whatever the work that the pump put into it. Do an energy balance around here. Is there any lowercase q going in or out of that pump? No, that's our standard assumption. And so the work that goes into the pump leads to an increase in the enthalpy of the fluid coming out. And then some other people said, you know what, I know how to calculate the work that goes into the pump. Let me ask this question. If you went from 20 kilopascal to 2 megapascal versus 20 kilopascal to 6 megapascal or 20 kilopascal to 8 megapascal, is the work the same regardless of the outlet pressure? Or does it take more work to boost it to a higher pressure? Which one is it? More work. More work to boost it to a higher pressure. So what's a nice simple equation for how much work per unit mass? I'm doing lowercase w, work per unit mass. That it has to go into that perfectly reversible pump, no irreversibilities, no entropy generation, to boost the pressure from 20 kilopascal to whatever the outlet pressure is. And if the outlet pressure is higher, you got more work. So what's that equation for WP? He's saying that the work is V P4 minus P3, or another way of saying V dP. Somebody says, you know what, I think I remember that this would be like the minimum or for internally reversible process. So if I have an open system, I have steady state flow, one inlet, one outlet, it's adiabatic. I can talk about that work, that if internally reversible flow through the system, no entropy generation. It could be a minimum if it's a shaft power going into a pump, or it could be a maximum if it's expanding something like a turbine. Okay, that would be minus the integral V dP. I know there's a change in kinetic and a change in potential, but almost always we neglect that. Does anybody remember this equation? Is that even in our textbook anywhere? Where is it at in our textbook? At the end of the chapter on entropy. Because you did entropy as a new property, entropy for a closed system, then entropy for an open system, and then you see combination of energy, entropy calculations for flow through open systems like a pump, where it's reversible. And you get a very startling result. This is one of the reasons, there's many reasons why thermodynamics is so hard. Because the first time you saw it, and I saw it on somebody's paper over here, they're saying, I think I remember that, but I learned that the work is the integral PDV. Yep, that's what I learned. Doesn't this equation look very familiar, integral PDV? And then all of a sudden, at the end of chapter 6, no. Integral VDP, no, something switched. Something's in the wrong place. There's a typo in the book. Is there a typo in the book? This is for a closed system analysis. This is for an open system analysis.
And it has to be reversible?
And it has to be reversible, exactly. But if you don't get that it starts for an open system analysis, you've lost. You've lost the game. You're confused. I don't understand why. Sometimes professor use U, sometimes you use H, sometimes CV, sometimes CP, sometimes, VDP, sometimes PDV. It's confusing. All right. Should anybody be embarrassed by having to go back into like chapter 3 and review a little bit, or into chapter 6 and review a little bit? It's at the end of the chapter 6 of this textbook, the last section. It's worth reading because they also talk about Bernoulli's equation. How many people remember Bernoulli's equation in fluid mechanics? Hey, we saw it in thermodynamics. It's a good tie-in. This engineering stuff, it works one class to the next. Anyway, so we have this integral VDP, and why can I then rewrite it like this? In what cases can I do that? Why for a pump, with putting liquid through a pump? Why can I rewrite it like that?
Water's considered incompressible.
Exactly. Water is considered a great incompressible assumption. It's a slight assumption that it's assumed to be incompressible, but it's a great assumption. And so if V isn't changing, it's constant. It comes outside the integral. Boom, there you go. What about this negative sign? Well, we're assuming that we know the direction of work into the pump, so we take care of it. But that negative sign corrects us for the correct traditional direction of the work transfer in a generic control volume. Okay? Remember this. When we get to gas power systems, we'll bring it up again. And so why do you have multi-stage compressors? With what happens in between the stages of a gas compressor? Intercooling. And that's to help bring that specific volume down, reduce the net work as you boost the pressure in a compressor. So this is a great concept. So I calculate H3, we know how to get that one, and we add V sub F P4 minus P3. That V sub F is evaluated at state 3, and it's assumed not to change between 3 and 4. Okay, so that's why I had this V column. I really don't need this specific volume until I get the specific volume of state 3. Then I use that to calculate, multiply by the delta P, and I get that specific work. In this case, I kept the sign on it so that it's consistent with the sign convention, and so it's a negative work of the pump. But when I add it, you boost. H4 is 8.12 kilojoules per kilogram greater than H3. Okay. Did I really use this number in the table? Not really. I just showed it that it's reproduced, that it's the same number. All right. How about in our steam tables without the use of software, can I somehow readily get T4? If it's in the compressed liquid table, yes. But I think the pressures that it starts for the compressed liquid table are so high that if you're not into that table, you basically just have to remember it's just a little bit more than T3. So add a half a degree if you really needed it, or a 1 degree. Or go get the software which will actually do this calculation to much more accurate. But it's a difficult task to get T4 out of our appendices. All right, let's take a look at our metrics for this cycle. Same boiler pressure, same condenser pressure. We just modified by putting a real pump and coming out of the condenser to be 100% saturated liquid. Look at this net work. That looks good. Look at the back work ratio. What percent is that? Is that 93%? No, that's 0.93%. That's less than 1%. That is really small. And you'll even see some people neglect the pump power to go back into a cycle. Don't do it for this class. But you'll even see that every now and then. That's less than 1%. We just neglected it in an analysis. I've seen that. All right? But it is less than 1%. What about this number? Thermal efficiency. How did it compare with the Carnot thermal efficiency? Did it improve the system or degrade the system a little bit? It degraded a little bit. Hold it. Why did the thermal efficiency from the Carnot, which was about 41.4%, why did it go down? Well, okay, what I'm going to do is I'm going to pause and walk around, and I want you to think of why that thermal efficiency went down. This is a metric we all agree. We would like to keep it as high as possible as a good engineer. Why did it go down? I'm going to pause, walk around, and hear your explanations. But I'm going to have to go fast. I need to phrase it, and I like it. That's the best answer so far, but in the interest of time, I got to press forward, right? What do we got? 4 minutes? So that's the best answer so far, is that the tie temperature isn't consistently high. From 4 over to 1, the fluid is changing. It's like I'm coming into this boiler right here. What temperature am I coming in at? Oh, about 60 degrees C. What temperature? Around 300 degrees C. Think about it going along a path. Well, it's got to get to 70, then to 80, then to 90, then 100, then all the way up. Hey, then finally can start changing phase from saturated liquid, 10% quality, 20% quality, all the way to saturated vapor. Now I'm out. So the temperature of the working fluid, one of the Carnot cycle, is it all had to be brought in at TH. Are we bringing in all of that heat into the working fluid at TH? Nope. We modified the cycle. Now we're bringing in a significant amount at a temperature a lot less than TH, between, let's say, 60 and, what was that temperature? I should remember it. 295, 300. So it goes to 295. And then we still bring in a lot of heat to go from 295 saturated liquid to saturated vapor. And right there is the Achilles heel. Why? Why?
Because it's not at
the thermal efficiency of the ideal Rankine cycle is definitely less than the Carnot. Why? Because of irreversibilities in the turbine, irreversibilities in the pump, irreversibilities in the boiler, or irreversibilities in the condenser. And one of those answers is the best answer. Which one is it? C, irreversibilities in the boiler. Is there a lot of friction in the boiler? Nope, the pressure didn't change. Inlet pressure, outlet pressure. Then what's the source of the irreversibilities? It's because anytime there's like 4 sources of irreversibilities that you're exposed to in Thermo 1. Friction, unrestrained expansion through a pressure change, heat transfer through a finite temperature difference, that's the key here, and mixing. Go back and look at those discussion of irreversibilities at chapter 5. right? Kind of memorize those, recite them to you. And the one here for what's happening in the boiler is the delta T. So we have our heat source. It's all at TH. It's all at 295. We have what's going on in the boiler. It comes in at 60. It goes out at 295. And over here somewhere it was 295. So in between saturated liquid to saturated vapor, it's fine. So right in here, what's happening? We have a large delta T between the working fluid and our heat source. That's the source of irreversibilities and the degradation. Thank you for your attention. We'll see you next time.